In this video, we're going to be talking about interest rate theory, more specifically, accumulation. So accumulation is the process of principal growth as a result of earning interest. So for instance, if at t equals 0, that is today, if we were to deposit $100 into an interest-bearing account, the question that we would want to have answered is, after n years of accumulation, how much is that $100 going to be worth? So to deal with this, we will often find ourselves using some terminology. Little I is commonly used to denote interest rate. Generally, when I am writing this stuff out, I will express it almost always as decimal points. I just find it easier to write 0.05 instead of 5%, or 0.1 instead of 10%, or 0.23 instead of 23%. It's easier to keep track of. Also, you will find little n. Now, this denotes the number of periods. Often it is denominated in years, however, it does not necessarily have to be. So basically, if n is equal to 25, all that really means is that we're compounding for 25 periods. It could be months, it could be years. That will be specified in the question. Now, t, the way that I like to think of t, that represents the time. So it's the point on your timeline. So generally, t equals 0 means right now at this very moment. So basically, when you think about it, it's 0 time has elapsed. So t is equal to 0. Now, you might have t is equal to 15, in which case we are looking at a point 15 periods into the future. Again, the periods can be denominated in years, months, or really anything that the question specifies. So the way that I like to do these sorts of questions, anything with the time value of money, interest rate theory, I like to start off a question by looking at a timeline, because they really help you to keep track of your work. So just as is the case with any timeline, you start left and end right. So the time on the left-hand side is going to be the time closest to you. The time on the right-hand side will be the time furthest from you. So for instance, if we had t is equal to 0, that is, again, right now at this very moment, and t is equal to 1, well, we just know that t equals 1 is 1 period into the future. So the number of periods that have elapsed in that given amount of time is 1 period. So n is also equal to 1. Now let's take a look at what happens if you don't start right now. Let's say we started at t is equal to 28. So this could be 28 days into the future, it could be 28 years into the future. However, the periods are denominated in the question, but for right now, we'll just leave them as periods. So we begin compounding in 28 periods, and we will end our compounding in 53 periods. So the gap between those is simply 53 minus 28 periods, and we would find that the number of periods in between time is equal to 28 and time is equal to 53. Well, that's just 25 periods. So now how does this all work when we're factoring in interest rates and money? So let's look at an example. So what is the value at t equals 1? Now that is 1 period into the future, and you can see right here that we're talking about annually. So 1 year into the future, if we deposited $100 at t equals 0, so that is right now, what is the value of $100 that we put in today? If it's earning 5% per year compounded annually, what will that be worth at the end of the first year? So again, we start off by drawing our timeline. So you could see that we start off with $100 at t equals 0. We earn 5% interest, and after 1 year, we want to know, what is this going to be worth? So what we do is we see that the $100 that we originally put in, well, that's going to be there in 1 year because we're not going to be adding to this, nor are we going to be taking money out of this over the year. We just want to know, we put $100 in, we leave it, what will that be worth? So that $100 gets basically passed through. But at the same time, it will also earn interest. And in this case, it's 5% per year. So we just multiply $100 times 5%, and we would earn $5 on the original $100 that we invested. When we add the two together, we see that at the end, it's really worth $105. That's how much our account will be worth in 1 year. Now, this is kind of a really long way of going about expressing that and figuring out that example. So let's do the same thing, except we'll use a little bit of a shortcut to try to help us make things go by a little bit faster. So again, same question. If we were to deposit $100 today that earns 5% per year, how much will that be worth in 1 year? Again, we start off the exact same way, except this time what we'll do is we'll multiply our original $100 times 1 plus I. So that is 1 plus the interest rate, and in this case we have 1 plus 0.05. And we multiply that by 100, and we see that we would end up with the exact same thing that we got in the last answer, which was $105. Now, moving on, that's great if we know what happens 1 year from now, but what happens 2 years from now, or 5 years from now, or 10 years from now? Well, we have what's called the compounding principle, and this happens over multiple periods of growth. And basically what it is, we earn interest on the interest that we've already earned. So in that last example, if we were to keep going with that $5 that we made in that first year would then earn its own bit of interest in the next year. And so what this really allows for is exponential growth of our principal. So let's take a look at a different example. If we were to deposit $1,000 today, and that was earning 10% per year, what would the account value be after 2 years? Now, what I want you to do is I want you to pause this video if you can, and I want you to think about it for a second and see if you can come up with an answer. Okay, so here's how I would go about doing it. First, we'll look at the really complicated way of looking at the initial amount and then the interest. So again, here we have our timeline. We can see that it has 2 periods represented there. Now we start off with $1,000. Again, because we're not adding or subtracting anything, it basically gets passed through. Now at the same time, we're going to be earning 10% on that original $1,000. So when we multiply 1,000 times 0.1, we can see that we earn an extra $100. When we add those two together, we see that our account value at t equals 1 is $1,100. Now again, we have $1,100 in our account. So as long as we don't add or subtract anything from that $1,100, that gets passed straight through. Now on that $1,100, we make interest. And in which case it's 10%, so we multiply 1,100 times 0.1, and we end up with $110 in interest earned in the second year. And now you could see that that's different than in the first year where we only earned $100 of interest. So now we actually made an extra $10. And when we add those two together, the original amount plus the interest earned, we see that we end up with $1,210. Now we can use the shortcut that we learned in the last couple slides, and we'll just do this on a year-by-year basis. So we start off with $1,000, and we multiply that times 1 plus I, which in this case I is equal to 10%. So 1,000 times 1 plus 0.1, and we see that that's equal to $1,100. Now that's the same account value that we had at t is equal to 1 as we did when we looked at it in this way. So now we take that $1,100, and this time we will multiply it by 1 plus 0.1 yet again. And when we do that, we see that we end up with $1,210, which is exactly what we had in this first example. But now there's even a shorter way of doing this. As long as our interest rates are the same from year to year, well, we can pretty much skip doing each and every one of these annual steps, and we can just do it all in once. So what we can do is we take 1,000 times 1 plus 0.1, and we take it to the second power. Now, why do we take it to the second power? That's because we're doing this over 2 years. So we have 2 periods, so n is equal to 2, and this is our n. So if we were compounding this for 5 years, this would be 1,000 times 1 plus 0.1 to the 5th power. If we were doing this for 10 years, it would be 1,000 times 1 plus 0.1 to the 10th power. Now, to show you what exactly the compounding effect really has, let's look at this example. Now, I went ahead and graphed it out in Excel, and if we were to compound this for 3 years to t is equal to 3, we see that it ends up at 1,331. Remember in the examples, we started with 1,000 right here, and then we moved up to 1,100, 1,210, and now 1,331. Now, if we keep taking this out further, you can see right now it's a pretty straight line. So the increases in gains that we're getting is not a huge amount. In the first year, we made an extra $10 off of interest. In the second year, we made an extra $11 off of interest, and it just slowly kept growing. But now what happens when we look at it even further out, you can see that we are increasing at an increasing rate. Now again, when we look at this even further, you can see that our account value is now growing much, much faster. So our original $1,000 at the end of 11 years is worth over $2,800. After 15 years, you can see that it goes up to nearly $4,300. Now, the really remarkable thing is when we take this way out, let's say 65 periods, 65 years, we can see that there is now exponential growth. We can clearly see that our account balance is growing exponentially. You can see that over 65 years at 10% per year, our original $1,000 is now worth almost $500,000. So to conclude this video, there's a couple things that we want to remember. Interest accumulation can be expressed simply as the principal amount, P, times the quantity of 1 plus I, the interest rate per period, to the nth power, where n is the number of compounding periods. Again, that could be years, that could be months, that could be days. Whatever the question says, that's how many times you compound it. Because n is the exponent, our principal grows exponentially over time. And that was why when we looked at the various charts of 10% per year compounding, we saw that in the later years, as we moved further and forward in time, that the account value became larger and larger.